Hi everyone. Today I, Divisha, along with my friends Komal, Preksha, and Purva, will be presenting our presentation on the topic Peripheral Component Interconnect, which is PCI bus.
Peripheral Component Interconnect, or PCI bus, the bridge that connects the CPU with various peripherals. It was developed by Intel in the 1990s to overcome slow communication in earlier buses like ISA or ESA. As you can see, the PCI bus acts like a high-speed highway carrying data between the CPU and devices such as sound, graphics, and network cards. It supports 32 or 64-bit transfers at 33 MHz, allowing up to 133 Mbps of throughput. The main need for PCI arose due to performance bottlenecks and lack compatibility in older buses. Its standardized device communication, simplified configuration through plug and play provided backward compatibility.
In the early days, PCI was used to connect internal components like sound cards and network cards to the motherboard. But as technology advanced, PCI became too slow and couldn't handle the increasing data speed required by modern devices. This led to the development of PCI-X and later PCI Express, also known as PCIe. PCI Express uses a serial point-to-point connection, unlike the older parallel PCI buses. If we look at the table, PCI offered around 133 MB per second bandwidth. PCI-X improved it to 1 GB per second, and PCI Express now provides up to 64 GB per second.
Core architecture of PCI bus. The PCI bus architecture is designed to connect multiple high-speed components efficiently in the CPU and the memory. So it consists of five key parts, which is the host bridge. It connects the CPU and the memory to the PCI bus segment, which is shared pathway for communication. The next is PCI devices, such as network or sound cards. Next is PCI to PCI bridges, which helps to expand the bus when multiple slots are needed. The next is Arbiter, which manages the access when multiple devices request control of the bus. The bus operates on parallel, shared, and synchronous designs, typically offering a bandwidth up to 533 MB per second. The data transfer happens in main two stages, which is the address phase and the data phase, which is controlled by signals like frame, IRDY, and TRDY, etc. The mechanism allows smooth burst transfer and supports direct memory access, which is the DMA, and handles interrupts efficiently, making PCI both fast and flexible for multiple connected devices.
The operation of PCI bus works through a series of well-timed handshakes between a master device and a target device. First, the master, usually the CPU, requests control of the bus through the request signal called REQ. The hashtag over here is the active low signal. The arbiter checks if the bus is free and when it is, gives permission using the grant signal. Once permission is granted, the master starts by activating the frame signal. It starts a transaction called frame. The placing address and command on the bus, the target device such as the graphics or sound card, detects the address and responds using the device select signal or dev cell. After that, the data transfer begins. The master indicates it's ready using initiator ready, that is IRDY, and the target responds with target ready or TRDY. When both of them are ready, one piece of data is successfully transferred. This process can repeat several times for burst transfers. And finally, the target sends the stop signal. Simply stop to end the transaction. So overall, the PCI is a coordinated handshake of request, grant, frame, ready, and stop signals. ensuring fast, reliable communication between all devices. The diagram that you see below here, that is address, then data, and then termination. The address phase starts when the master places the address and command on the bus. Then, during the data phase, information is transferred until the termination process or the phase ends the transaction with a stop signal.
Today, there are several types of PCI connections used for different purposes. Mini PCI Express is used in portable devices and laptops because of its small size. External PCI Express, also known as Thunderbolt, is used for external GPUs and high-speed storage. These interfaces are also electrically compatible, supporting both 5-volt and 3.3-volt systems, meaning newer devices can still work safely with older hardware.
Let's look into the device configuration and electrical characteristics of PCI bus. Each PCI device has a configuration ROM storing its ID and details. When the system starts, firmware reads their ROMs, performs enumeration, and assigns memory and input-output addresses so every device communicates without conflict. The PCI bus works on 5-volt or 3.3-volt power depending on the motherboard. To ensure compatibility, are keyed so that only matching cards can fit. We have an example of the 5-volt and 3.3-volt boards. Overall, this configuration and electrical setup gives PCI its famous plug and play capability and stable performance.
Coming to the advantages, the PCI bus provides high data transfer rates compared to older buses like ISA, supports plug and play, and maintains backward compatibility. It also allows multiple devices such as graphics, sound, network cards to share a common interface. However, PCI bus does have limitations because all devices share the same parallel bus, the bandwidth is divided among them. At higher speeds, signals can interfere or crosstalk, reducing reliability. This is why the industry gradually moved to PCI Express, which uses dedicated serial lanes or for each device.
Now let us move on to real world applications of PCI bus. So firstly, we have graphic cards. PCI slot powers GPUs for gaming, AI and designing, which is very useful. Next come the sound cards. It enhances the quality for professional music and studio system. Network adapters, we must have seen it in LAN, Wi-Fi and 5G expansion cards use PCI for high speed connectivity. Next come the storage controllers and SSDCs. So we often see them for ultra fast data access and transfer to capture and video cards used for live streaming, broadcasting and security system. Then next is industrial and embedded system. PCI is still used in automation control units and legacy environments.
The future of PCI technology looks very exciting. The next generation PCI Express 6.0 and 7.0 will offer data speeds up to 512 GB per second, which will power advanced fields like AI, machine learning, and 5G communication. PCI Express is also now working together with a new technology called CXL, Commute Express Link. This allows CPUs, GPUs, and accelerators to share memory directly, making system faster and more efficient. Finally, with the growing focus on green and sustainable computing, the PCI standards are evolving to become not only faster and smarter, but also more energy efficient.
These are the sources we refer to for understanding technical aspects and evolution trends. This wraps up the background of PCI and sets the base for the architecture ahead.
To conclude, the PCI bus revolutionized computer hardware communication, making expansion and compatibility simple. Its design paved the way for PCI Express, which now powers modern GPUs, SSDs, and AI accelerators. In short, PCI is the foundation that will shape how devices talk to each other today. Thank you.